Hey guys, welcome to quantum mechanics again. Hope everybody's doing okay. Hopefully everybody's watching the videos. If you're having any problems or technical difficulties, let me know, and I'll be happy to take a look or try to fix things. And let me know if I fall behind as far as putting the notes in the Dropbox, because I've got a lot of things going on, so sometimes I might forget. Um, and hopefully I won't forget to record these lectures ever, but if I do, don't hold it against me. uh, so, right, the homework, today is, well, it's Tuesday night, but so the homework's due on Friday, I think. And, I had said that, if you wanted to uh, type it up either using a word processing, type of program, which I wouldn't highly recommend, or using LaTeX, be, worth your time and effort as far as grade goes. Um, for those of you that want to learn LaTeX, I've actually put an example LaTeX file in the Dropbox. It's in the docs, DOCS file. So if you want to have a look at that. And, what most people do is just kind of hack their way through learning LaTeX. There's not a real, good tutorial or, any way to really learn it besides just starting to do it and, just practice. It's a lot of trial and error, and you'll find yourself, spending 20 or 30 minutes looking for an open curly brace or a dollar sign or something, crazy like that. But it's just all part of the training and part of the fun of being in physics. Okay, so last time we wrapped up our first topic in approximation methods, which was the variational method. And honestly, the variational method doesn't really see a lot of use that I know of in modern physics. I think it's more used in chemistry and things like that. The real workhorse, as far as approximation methods go in physics, is perturbation theory, and that's what we're going to spend quite a bit of time talking about over the next couple weeks. And the perturbation theory, use of perturbation theory, has applications in all types of physics. It's one of my favorite topics because it's extremely important to high energy physics, where the Hamiltonian itself is so complicated. Well, it's complicated enough that you can't solve it exactly, and so you have to resort to approximation methods. And it turns out that perturbation theory works extremely well when you're trying to calculate observables. And I know it has uses in condensed matter as well as nuclear physics and things like that. So it's a really important topic, and hopefully you know um, we'll have some fun learning it. Okay, so the use of perturbation theory is it's really convenient, like we've talked about before, when you have a problem that depends on a Hamiltonian that has a familiar piece to it. And by familiar, I mean that a piece of the Hamiltonian that by itself we know the exact solutions for. All right, so in terms of an eigenvalue equation, we could break the Hamiltonian down into some piece that I'll call H0 and another piece called H1. And H0 would be the piece that we would know the solutions for. So it could be like the subharmonic oscillator or the Coulomb potential or something like that. And we know what the form of the eigenvalue equation would be. So in this simple case, we would just have some eigenkets that we call E naught, and so the eigenvalue equation for what I like to call the simple piece. This it's not necessarily simple, but it's simple, and the fact that we know what the, we know how to solve it. And so that takes care of part of the Hamiltonian. The other part, the H1, is what we call a perturbation on top of uh, the, the simple Hamiltonian. And by perturbation, I mean a small kind of fluctuation on top of H0. So H0 would be responsible for a large the large effects as far as the energy spectrum goes, and H1 would just be small fluctuations on top of that. Okay, and so we this is called perturbation theory, and I'll show you how we develop it. Just to introduce some vocabulary again, H0 is the simple Hamiltonian, or whatever you want to call it. It's the unperturbed Hamiltonian, so it's the piece that we know the solutions for. And H1, I'll call it a lot of times the perturbation on top of our simple piece. Typically, 99% of the time, we're going to only consider cases where H1, the perturbation, only depends on the position operators. Okay, but even in that case, where we restrict ourselves to position operators or functions of position operators, H1 can take several different forms, and we're really left with several kind of types of situations that we have to deal with. The first one is the one we'll tackle first, and it's called time-independent perturbation theory. And time-independent perturbation theory can be broken into two sub categories. One is the case where you don't have any degeneracies in your energy spectrum. All right, so that's what we call time-independent, non-degenerate perturbation theory. All right, and like I said, non-degenerate means that that there's only one state that corresponds to some particular eigenenergy. So there's no two states have the same energy, and you'll see why a little bit later why we have to break time-independent perturbation theory into these degenerate and non-degenerate cases. Okay, so we'll spend a lot of time talking about time-independent perturbation theory and solving some different problems, and then we'll move on and talk about time-independent degenerate perturbation theory. So this is a case where you have degeneracies, and you have to somehow figure out how to work around this, or how to incorporate the degeneracies. And what we'll see is that the perturbations typically, if they're strong enough, will lift these degeneracies. In other words, it'll split those common energy levels into 2 or 3 or however many degenerate states there are. Okay, and then the final topic that we'll cover in perturbation theory is time-dependent perturbation theory. And that's where you have a Hamiltonian that depends on time, and the time dependence is contained in your perturbation. And so we'll see plenty of examples of that. And that'll actually lead us into a discussion on scattering theory, because you can kind of picture a scattering as a time-dependent perturbation on a system. Okay, and we'll see how that works. Okay, so those are the three main topics of perturbation theory. So let's start talking about time-independent perturbation theory. Okay, so we'll lay down some formalism today in this lecture. We'll get most of it, and then next time we'll pick up and finish off the formalism and start to talk about some concrete examples. Okay. So again, here we're assuming that we have a piece of the Hamiltonian that we know the solutions for. And just for shorthand notation, I'm going to replace the eigen values or eigenkets of that Hamiltonian, H0, and just write them as N0. Okay. And the basic assumption is that for every eigenket of the unperturbed Hamiltonian, there's going to be an eigenket of the perturbed Hamiltonian, the full perturbed Hamiltonian. Okay, so this thing H is what is made up of H naught plus H1. Okay, so that's just saying that, if you start out with 5 eigenstates, and in this time independent non-degenerate perturbation theory, when you apply the perturbation, you're still going to have 5 eigenkets. Okay, they might be slightly rotated or something like that, but there's always going to be the same number of eigenkets as what you started with. Okay, and the basic assumption in perturbation theory is that we can come up with solutions for the full Hamiltonian in an approximate way by expanding or assuming that we can expand both the eigenkets and the eigenvalues of the full Hamiltonian. Okay, so this is what I have here. So the n here would be the full eigenket, the eigenket for the full Hamiltonian, and we're assuming that we can write it as a perturbative expansion. Okay, so this n naught would be what we would call first order or leading order. This would be a next to leading order or the first order term, second order term, and so on and so forth. Okay, so the 0, 1, 2 here, they're not powers, they're superscripts. So they're basically counting. They're there to keep track. They're kind of bookkeeping notation to let you know what order of perturbation theory you're in. Okay, so typically what we'll do is we'll have some small parameter that'll be multiplying our perturbative term or perturbative Hamiltonian, and we'll expand in that small parameter. Okay, so the hope is, when you do perturbation theory, that n0 is going to be your leading term, and n1, because it contains 1 power of that small parameter, is going to be smaller than n0, right? And by small, I mean less than 1, right? Between 0 and 1, a fraction. So n2 would contain 2 powers, and because your small parameter is small, when you square it, it's going to be getting even smaller. Okay, so the goal or the hope is that at some point you can just cut this perturbative expansion off and obtain a fairly accurate solution for both the eigenkets and the eigenenergies. Okay. So, like I said, a term with some superscript k, the vocabulary is, we would call it the kth order term. Sometimes you'll hear me, and I think I already did, call this the leading order term, next to leading order term, next to leading order term. That just comes from my background in quantum field theory. So, you'll probably hear me say that, but I'll try to keep with this kind of kth order, so 0th order, first order, so on and so forth. Products where you have different superscripts, so like if we had some case where we had some energy term with a superscript k and it's multiplying an eigenket with a superscript k bar, we would call this the k plus k barth order term. Okay, so in other words, the superscripts add together. Okay, so they're counting what order you are in perturbation theory, and so they always add if you have products of these terms. Okay, and like I said, the hope is that in using perturbation theory, that these terms, as you go up in order, get systematically smaller. Okay, so if that's not the case, then obviously perturbation theory is not a good technique for the problem you're trying to solve. Okay. Let's see. Okay, so let's try to find some terms in this expansion for the eigenket n and the eigenenergy E sub n for the full Hamiltonian. Okay, and we'll do this kind of like in a bootstrapping way. So we'll basically build it up from the ground level. Okay, and so we're going to start with the eigenvalue equation. So this is a definition. So we know that there's some eigenbasis, right? That when the Hamiltonian hits it, gives us an eigenvalue. and the eigenket back. Okay, this is the definition of the eigenvalue equation, where here the H is the full Hamiltonian. So it's the 0th order, or the unperturbed, plus the perturbation term. Okay, and so what I want to do is take equation 3, which is this guy, right, and equation 4, which is this guy. So we're taking our perturbative expansions and plug it into this equation, okay? And what we'll do is we'll plug those in. So we'll have an expansion for this guy over here on the left-hand side. And on the right-hand side, we'll have two expansions, one for this guy and one for this guy. We'll multiply out the terms, and then we'll collect like terms. So in other words, we'll collect the 0th order terms. That'll give us one equation. We'll collect the 1st order terms, and so on and so forth. Okay, so let's see how that works. So let me take those expansions and plug them in. Okay, so for here, H, I've got the full Hamiltonian, H0 plus H1. Here's on the left-hand side, N, I'm expanding it to second order, right? So 0 first, second order, plus dot, dot, dot. Equals the right-hand side. So here, E sub N, I'm expanding it in terms of E0 plus E1 plus E2. And the same thing here for the N on the right-hand side, I'm expanding it up to first order. Okay, so now we want to take this and we want to multiply it out and match terms. Okay, so we multiply out both sides, and I can see the 0th order term would be this H naught multiplying N0 on the left-hand side, and on the right-hand side, I've got En0 multiplying the ket N0, and that's just the 0th order, the leading order eigenvalue equation. Okay, so that's what we already knew. All right, so that's the solution for the simple piece. Okay, and as we would expect, it's independent of the perturbation, so we call it 0th order in H1. Okay, so now what we can do is we can match, from this equation, we can match first order terms. Okay, so we can look at this guy on the left-hand side, and I'm going to have two terms, right? I'm going to have H0 multiplying N1, and I'm going to have H1 multiplying N0, right? And likewise over here, I'm going to, on the right-hand side, I'm going to have two terms where En0 is going to multiply N1, and where En1 is going to multiply N0. Okay, so let me write those four terms out. Okay, and what we want to do here is we want to try to simplify this, right? And one way we can do that is to use the fact that we know what the eigenvalues of this guy are, right? And it's a Hamiltonian, so we know they're Hermitian. Okay, so what I can do is multiply from the left by an eigenbra of the H naught Hamiltonian, right? So when I do that, I would get an equation that looks like this. So I've got N0 hitting H0 over here, right? This guy, we don't know anything about it yet, okay? And then the N0 on the right-hand side would pass through these energy eigenvalues, right? So I would get the overlap of N0 and N1, and here I have the overlap of N0 with N0, right? So we're assuming that these guys are normalized, okay? So that means that N0 on N0 just gives me 1, and over here I can evaluate H0 hitting N0, right? That's going to give me the eigenvalue En0, right? And leave me with the overlap of N0 and N1, okay? But that term is the same as this first term on the right-hand side, okay? So those two terms will cancel out. And what I find is an expression for the first order energy eigenvalue, or the correction to the energy the first order correction to the 0th order energy. Okay, and what you see is it takes a very simple form. It's basically the expectation value of the perturbation Hamiltonian with respect to the unperturbed eigenkets. Okay, so it would be the diagonal elements, if you will, of H1. Okay, and that's it. That's as simple. That's as difficult as it gets. It's pretty easy, right? It takes a nice simple form, right? And it's an important expression, so that's why I put it in a double box, okay? So the first order energy correction is just the expectation value of the perturbation Hamiltonian with respect to the unperturbed kets, okay? So play that back and, over and over until it's burned into your mind, okay? All right. Yeah, I just said that. Okay. And we see, as expected, I was careful to keep track of these superscripts, and we see that the first order energy shift, or the first order energy correction, is proportional to 1 power of the perturbation. Okay. All right. So that's always a good kind of check, just to make sure you're doing your bookkeeping correctly. Okay. So now, so we know something about the first order energy eigenvalue. Let's see if we can't find the first order energy eigenket. Okay. So there, what we want to do is we want to go back to our first order equation. This guy, equation 8. Okay. And now we've multiplied by an eigenbra of H0, right? And used the particular one, we called it N0, right? So it was the eigenbra of this guy. Now what I want to do is multiply by an eigenbra again of H0, but this time pick an eigenbra that's perpendicular to this guy, right? Okay, so that's what we want to do. So we do that, okay, and what it allows me to do, again, is to evaluate this term over here because I know what H0 hitting M0 does, okay? And so that leaves me with this matrix element here on the left-hand side. On the right-hand side, the M0 passes through, again, our energy term, hits our first order energy eigenket, and here I have M0 hitting N0, right? And by definition, we said that they were orthogonal, so this term is going to drop out, okay? And so what do I have here? So I've evaluated the the 0th order Hamiltonian, right? So I get M0 on N1, which we don't know, okay? We don't know what N1 is, so that's what we're after. And over here I have M0 and N1, okay? And you notice that the subscripts on the energy terms are different, right? Because this guy came from H hitting M, and this is the N that was in the initial equation, okay? So we can at least solve for this overlap of M0 and N1 by taking one of these terms over to the other side. So it looks like I'm taking this guy over here, right? And then I have this matrix element, which I don't know yet, but it is a matrix element with respect to the unperturbed kets. So it would be calculable. Okay, so that leaves me with this coefficient M0 and N1. Okay. So we know that M here is perpendicular, is not, it's not N. Okay. So what it's telling us is that this equation determines all the components of this N1, the guy that we're after, in the eigenbasis of H0, except for the N1 piece that's parallel to our 0th order ket. Okay. All right. And we're going to call that guy, the parallel piece, we're going to call it N1 parallel. I know it's imaginative, but that's what we'll call it. Okay. So what we want to do is try to determine this piece. Okay. And to do that, we're going to try to require in other words, the all orders eigenket to be normalized to this order. In other words, what I mean here is that when I take n and sandwich it with n, right, that we're assuming that these guys are normalized. And I realized that after looking at this, I have a typo that here, when I expand to first order, I should have a factor of 1 over square root of 2 in front of both of these terms. So the overall factor should be 1/2. Okay. So that's what we have. Okay. And now what I want to do is write M1 in terms of N1 perp, the perpendicular piece, to the unperturbed cats plus the parallel piece. Okay. And I do that in both of these terms, both of these factors. And then I multiply out. Okay, so I multiply this out. N0 on N0 gives me 1. N1 perp on N1 perp gives me 1. All right, but remember there's a missing factor of 1/2 out here. So that changes that 2 to a 1. And likewise, I get some cross terms between N0 and N1 parallel. All right, so these two cross terms. Okay. All right. And I've dropped all terms where N0 hits N1 perp, okay, as well. So what it's telling us is that these ones cancel, okay? So it's telling me that the sum of N0 on N1 parallel plus N1 parallel on N0, in other words, the complex conjugate of the first term, the sum of these two guys, vanishes, right, when I drop the higher order terms. Okay, so what that's telling me is that these guys they have to be complex numbers, right? So in other words, N0 plus N1 parallel I can write as I alpha, where alpha here is real, and we're going to assume that it's some small number. Okay, so it's kind of like our perturbative counter. Okay, so this thing is first order in some small parameter, and we're going to call that small parameter alpha. Okay, but what this equation is telling me is that these guys are complex numbers, or they're purely imaginary numbers, right? So that when I take the complex conjugate of this, I get minus, and so the two terms will cancel each other out. Okay, and let me come back to this for a second. All right. Okay, so let's try to see how we can use this. Okay, so let's go back to our the original expression for n, right, which looks like this. It's n0 plus n1. Okay, and in front of this n1 term, I'm going to multiply by 1 in the form of my completeness relation. Okay, where the completeness relation is in terms of the unperturbed cats. Okay. And what I want to do is pick out the one term. So m here runs over all values of however many unperturbed cats you have. One of them would be the n eigencat. All right, so what I'm doing here in the next step is pulling out that first, or that term where m is equal to n. Okay, so that would be this first, one of the terms coming out of here. And then what's left is the same expression, but now I've picked out the m equals n case. Okay, so that guy is out here in the second term. All right, and now I want to take my expression for n1, which, in terms of parallel and perpendicular pieces to the unperturbed cats, and expand that out. Okay, so let me plug that expression in. All right, so this gives me the n naught on n1 parallel, right, which we don't know yet, and n naught onto n1 perpendicular, and by definition that term is 0, so we can drop that, and we're still left with this summation term here. Okay, so now what I can do is use our the expression that we kind of derived for this term, this n naught on n1 parallel. Right, that goes back to here. All right, so n naught on n1 parallel we said has to be some imaginary number, and we'll call that imaginary number I times alpha. Okay, let me get back to where we were. Okay, so I'm replacing this guy with I alpha. All right, and then here I'm using the expression that we found for m naught on n1. Remember, it went like this matrix element of h1 between m and n divided by the difference in their energies. And this, by the way, is why we have to split degenerate perturbation theory from non-degenerate perturbation theory, because in degenerate perturbation theory, as you sum over these eigenkets or eigenvalues, you would hit cases where n equals m, and this thing would blow up. Okay, and that's obviously not a good thing. So that's why we have to treat the degenerate case a little in a little more special way. Okay, so I have n naught plus I alpha times n naught plus this junk over here, right? And so this is like 1 plus I alpha times m naught, right? And I said that I alpha is small, so what we can do is kind of resum it, right? So I have 1 plus I alpha, and that's approximately e to the I alpha, right? If you think about expanding out this e to the I alpha. Okay, so I can kind of group that together, and I get n naught times e to the I alpha plus this stuff, right? And now I can always multiply, by an overall phase, right? So this is the guy that we're after, the full eigenket, right? But it doesn't matter if I multiply it by an overall phase, because, all we care about are, probabilities and not screwing up things like normalizations and stuff. And so if I multiply this by a pure phase like this, an overall phase, it's not going to screw up anything, because when I take the sandwich, you'll say n with a n bra, the n bra would come with an e to the plus I alpha, and they would cancel each other off. Okay, so I can multiply this full thing by e to the minus I alpha. All right, so that's going to cancel the e to the I alpha here. I'll get an e to the minus I alpha over here, and an e to the minus I alpha on this term. But e to the minus I alpha times n, we can just call it n, right? We can just absorb it into the definition of the eigenket. Right, so what it leaves me with is n is equal to n naught plus this junk being multiplied by e to the minus I alpha. Right? And what I do next is, okay, so this guy, again, remember alpha is kind of like our counting for our perturbation, right? And this guy is already first order, right? It already has one factor of h1 in it, okay? And so that means that if I expand this guy out, I'm interested in computing this thing to first order. So that means that I can drop the term that goes like I alpha, right? Because that term I alpha times this piece would be second order. So what I can do is just say, okay, all I need out of this guy is the 1, right? So I can just set it equal to 1, okay? And so what that tells me then, finally, is that n1, which if you think about the way we wrote down n, the full n up to first order, so it was equal to n naught plus n1, right? So it's telling me now that n1 must be this stuff, okay? So this sum over m, where m can't be n naught, of this matrix element divided by the difference in energies and multiplying the unperturbed eigenkets. Okay, so n1 takes a nice compact form that looks like this. Okay, so that's the formalism up through or up to first order. I think next time what we'll probably do is talk about second order corrections to the energy. Maybe talk about second order corrections to the eigenkets. Typically, we don't really need those, so I might just skip it and just focus on second order corrections to the energy, and then hopefully we'll get into some cool examples. Okay, so if you have any questions about anything, again, don't hesitate to email me. Email me on my Gmail account, because I'm really slow on the UTA account. Okay, so make sure you email me on the Gmail account, and I'll get it, and I'll try to respond quickly. Okay. All right. So good luck on the homework. Let me know if you have any questions, and I'll talk to you soon. All right.